Okay, so we're on to our next speaker. So the next speaker is Isabel Valera. Isabel, are you there? Yes.
Yes.
Thank you. So Isabel is a full professor at the Department of Computer Science in Solent University, and she's a group leader at the MPI for Intelligent Systems in Tübingen, where lots of amazing machine learning has happened in the past, and I'm sure she's doing more amazing stuff now. And her research focuses on developing machine learning methods that are flexible, robust, interpretable, and fair in the normal sense, not in the data science sense. She's going to talk about algorithmic recourse from counterfactual explanations to interventions. So over to you, Isabel.
Thank you for the kind introduction. So, can you see my slides?
Perfect.
Okay, so in today's talk, I'm gonna actually talk about some of our recent work, which falls into the topic of ethical machine learning, and in particular, we are gonna talk algorithmic recourse. For those that are not familiar with that topic, don't worry, I'm gonna introduce this, the definition of algorithmic recourse. So, as probably many of you know, nowadays we have machine learning systems to inform or even to replace human supervision in a wide variety of decision-making processes. And some of these decision-making systems, they make decisions which I call consequential, as they may have important or significant impact in the life of the individuals that they decide about. So one of the main worries that not only we researchers have, but also some of the governmental entities and civil associations, is that how do we make sure that the outcomes of these automatic decision-making systems are aligned with human goals and values? So here I place some of the examples that we can see if we consider all the stakeholders that are involved in a decision-making system, starting for the deployer, all the way to the final individual that we are making the decision about, and overall the society or the justice system. They all have different goals or different objectives to fulfill. And something that might be a spoiler, but I think is quite clear by now, is that actually answering all these questions, like the examples I place here, requires significantly more information than simply training the machine learning system to maximize accuracy. And in today's talk, what I'm gonna do is to give a concrete example of which kind of additional information and challenges we face when we try to answer some of these questions from the perspective of interpretable machine learning. So here we have a definition of interpretability provided by Finalidos, Cibeles, and Bim Kim, which is simply the ability to explain or to present in understandable terms to a human. And what we are trying to explain in our case are the decisions made by an algorithmic decision-making system. So if we focus in the final individual that is affected for the decisions by the system, let's say in a scenario of loan approval, these individuals might wonder why they didn't get the loan and what should they do in order to get the loan next time they apply. So a potential answer to such a question might be, you were denied the loan because your salary was 25K. If your salary would have been 30K, you would have gotten the loan. And this kind of explanation provided by the ML system is what in 2017, Sandra Wachter and her collaborators introduced as a counterfactual explanation. But in this same paper, the authors also state that the need of explanations to help individuals to act in order to correct their situation rather than just to understand. Motivated by that concept is where we can define the concept that we are going to focus today, which is algorithmic recourse. and which is defined as the actions required for, or in general, the systematic process of reversing an unfavorable decision across a range of counterfactual scenarios. So if we look formally at the definitions of these two concepts in the context of machine learning, what they have been is to be written as optimization problems. So in the case of counterfactual explanations, what they have defined is the nearest counterfactual, which is no more than the most similar individual to the one that is seeking for recourse that would get the desired outcome. So we are finding here the individual, the most similar, given a similarity or distance metric, that would get a different outcome than the individual, the factual individual seeking for recourse. This formulation may have some additional plausibility constraints to, for example, account that the counterfactual explanation, which is this X CFE that I place here, are in high density regions with respect to the data distribution. A couple of years later, Hudson and his collaborators, what they did was to replace this counterfactual explanation problem into one that focused more on the actions that the individual needs to place in order to achieve recourse or their favorable decision. So that now what we are trying is to find the minimum, the set of actions, where here we measure as shift in the features of the individual, that a minimum cost will ensure recourse. Something that is important from this new reformulation is that by writing the problem in that way, we are able to add new constraints, which we call feasibility constraints, that account, for example, for the actionability of the features. To prevent, for example, that we require an individual to change their gender, or to decrease their age in order to get the desired outcome. Something else important here is that the main assumption that this new reformulation is doing is that we can get the counterfactual explanation or the new feature vector in an additive way, given the original feature vector for the individual seeking for recourse, and we also have the vector of shift in these features. However, as we are all aware, in general, the features that we collect from the individuals, they are not independent from each other. So if we consider that we have collected X1, which is the salary of the individual, and X2, which is the savings of the individual, it is well known that a home seeker tends to save 30% of their salary in order when they are looking for a house. So these kind of dependencies between features can be captured using a causal model, which we represent here with this set of what we call structural equations that relate the different observable features with unobservable features or non-is variables, and can be additionally represented using a causal graph. So what we also know is that once we are given with a causal model, the way we perform actions in such causal model is through interventions. So what we can do is to rewrite the counterfactual-based actions that we got from solving the optimization problem in the slide before, and was giving us a delta, a shift in the vector that would trigger recourse, hopefully, as an intervention where, in addition to define this delta, the new value of the variables would be therefore the original value plus the delta. We need to define the set of variables for which we will intervene upon, which in this particular case we define as those variables for which we are going to change their value. So as an example, if we have recommended the individual to increase his savings by $5,000, that is a 20% increase with respect to the original value, what we will obtain is this new causal model where now we have broken any dependence between X2 and its parent X1 to fix its value to this particular value. However, once we see the original causal model and the post-intervention or post-action causal model, what it is easy to observe is that actually we can do better. And we can obtain an action or an intervention now that by only increasing 14% the salary of the individual will due to the causal dependencies, it also increased by $3,000 the savings of the individuals, and that would directly give ensure recourse to the individual according to this classifier that we got here. So the first result that we can see here is that actually counterfactual explanation-based actions might lead to suboptimal recommendations for the individual to change their situation. But the limitations don't restrict to that example, but they go beyond that. And in particular, our key theoretical result in our original work is that a counterfactual explanation-based action is in general only going to guarantee recourse if and only if the set of descendants of the intervene upon variables, which are here, and we defined before, is empty. That means that we can only intervene on variables that don't have any children according to the causal graph. So how does this key result translate in practice? Well, we either need that while generating the counterfactual explanation-based actions, all of our features in the causal model, in the true causal model, are independent from each other as represented here, so that we can intervene on them without having any impact on the other variables. Or since this assumption is highly unrealistic because we usually don't collect information about individuals that are independent from each other, we can alternatively force independence by intervening not only on those variables for which the shift is different from zero, but also on all its causal descendants. The problem is that, as we have seen before, this approach might be suboptimal, as in the example of the previous slide, or directly infeasible, as we are requiring to be able to intervene on every variable, almost every variable in the graph. So what in our work we did was to actually rephrase the optimization problem for recourse to directly account for the set of interventions that at minimum cost will result in resource. And of course, here what we do is to directly account for the structural counterfactual that directly accounts for how the structural equations will change once we perform an intervention. So here we are having the original structural equations and the post-intervention structural equations. I'm not going to really enter in details, but basically for those familiar with Pearl's book, basically what we can do is to run the abduction action prediction method to compute the counterfactual value of every variable after an intervention. The main problem of this new formulation is that here we are assuming that we have the structural equations, actually it's inverse, in the true model. And we have a bit of a negative result, which is that actually algorithmic recourse can in general only be warranted if we have the true structural equations. Irrespectively of how much data, either observational or experimental we are going to need the structural equations and the shape and the value of the coefficients. And this is unfortunately not available in the real world. So what we afterwards did was to propose two approaches where we relax the assumption of having access to the true structural equation. And in the first one, we simply assume that we don't know our structural equations, but we assume that they are of the additive form, additive Gaussian, where we have here the additive Gaussian noise, and here we have the form of the structural equation, which we don't know. And what we do is to actually estimate the counterfactual distribution by averaging over an infinite number of structural equations using a Gaussian process, where now this additive Gaussian model for our structural equations is going to be captured with a Gaussian process. As a result, what we can do is that instead of the standard case as proposed by Pearl, which does the abduction action prediction step in a deterministic way, we can do it in a probabilistic way. And of course, we can now rewrite the recourse optimization problem as shown here, where now it doesn't make sense to check whether the classifier output is going to change, but whether in expectation with respect to the counterfactual distribution is going to change. And the good news is that also we can play with this threshold that we want to pass to account for how much of the probability distribution mass, the one I represent here with this orange cloud, needs to be on the positive side of the boundary, which I represent like above this line. The problem of this approach is that, of course, we depend on whether the structural equations are of the form of additive Gaussian noise. And this in general might not be the truth, but it's even non-testable. So what we did in the next step was to go one step beyond and really not make any assumption on the structural equations, but simply say that we have causal sufficiency. That means there are no confounders between observable variables. So in that particular case, what we can now do is to estimate the effect of an action or an intervention in a subpopulation that is similar to individual seeking for recourse. Not directly on the individual, but on a subpopulation which is similar to him, and I represent here with this orange cloud. And for that, we can use the interventional distribution, which can be computed as shown here, where basically it factorizes across any known condition on its parents distribution. This approach resembles the conditional average treatment, which has been used to, for example, predict the effect of a drug in a population suffering from a disease. But in our case, we can rewrite also the optimization problem of recourse as before, but now it is key to notice that here, instead of having the counterfactual distribution, we have the interventional distribution. I don't think I have too much time to go in details, but we have run a lot of semi-synthetic experiments, and there are like a couple of key messages that I think we can observe in these examples by comparing the validity, whether the proposed action by the different methods leads to actual recourse for the individual and the cost of these actions. And what in general we observe is that the probabilistic recourse approaches, the two I just presented before, tend to be much more robust than if we make use a point-based regressor to fit the counterfactual distribution. The second message that we need to come across is that while the subpopulation-based approaches, the ones based on conditional average treatment effect, lead to lower validity at a higher cost than individual approaches. This is obvious, as we are trying to move not only the uncertainty about an individual, but about a whole population to the other side of the boundary. They also tend to be more consistent in the type of actions or interventions that they propose. Actually, at the moment, there is a disagreement or a mismatch in the individualized approaches with the true causal model. They tend to propose actions that are completely different between different methods, when this is not the case in the case of population-based approaches. So just to conclude, as we have seen in other topics in the literature of ethical machine learning, it is necessary to have some knowledge of the causal model underlying in our data. This is, in general, having fully information of the causal dependencies is unrealistic, and what we are doing currently is to see how can we relax these assumptions. And of course, we have also seen that in general, there is always going to be a trade-off between how strict our assumptions are and also how individualized the recommendations of the results that we can provide are. But I think we are moving in the right direction, even though there is still a lot of future work to be done. Here I mentioned a bit. So if you are interested in knowing a bit more, or all the details I skip in this talk, the preprint of the 2 works I presented is available here, and I'm happy to answer any question. Thank you.
Thank you, Isabel. Apologies if there's any banging going on. I think my kids have just started some sort of class upstairs, but okay, so let me have a look if there's any questions. So I can't see any questions. So as I said, if anyone wants to just jump in with a question now, then speak up. So okay, I'm going to ask, because causal inference has been kind of extremely hot topic in medical sort of areas, in applications, and people are really interested in terms of prediction models in healthcare. And I really like this idea of kind of bringing probability to the causal, bringing in the uncertainty into the causal side, and thinking about actions using these causal inference systems, because we use these prediction models to then actually do things. But often when we're trying out in medicine to do things, we might do it with trials. And in trials, you can also select your data in a sense. You can kind of, so you want to know about causality, you want to take actions, but you also, in smart trials, you can also select the data on which you're going to start doing investigations and taking actions. Would that fit into this framework? Could we also fit in kind of the active selection of data on which to try actions with causal inference? Or is that just getting too crazy to combine all those things?
I actually would say so. So I haven't entered too much in the discussion in here, but how the data collection process is being performed is a key factor in any ethical issue of machine learning. So in that regard, you only don't need to account for which distribution you are sampling from, but also what are the features that you are collecting and how they relate with each other. So I believe that whenever you are trying to deploy or develop a system that is in the context of either healthcare, but also any other consequential decision making, we are gonna need to, from the beginning of the process, to have a more broad or holistic view of the system, starting from which features we collect, and whether, for example, we can even draw a causal graph between the feature up to some extent.
Yeah, because I suppose you can select data where you have a stronger belief in your causal relationships, for instance, and then it's kind of safer to make inferences in that class of data. So like a subpopulation where you believe your prediction model is really describing things correctly, whereas the general population, maybe the causal uncertainty kind of leaks in a lot more. I guess it might be very hard to do, but it sounds really cool to combine all these ideas.
Yeah, well, in some applications so far, what we are assuming is that the causal graph can be extracted with prior knowledge of the expert in the field of application. But I guess in the long run, it would be during the whole decision or design of the system, of the machine learning system, they would directly need to do very carefully the data collection and try to see what kind of information beyond the feature collection and the maximizing accuracy they can draw. And this is also gonna limit how many ethical warranties they are gonna have. So I think they are gonna need to probably keep it in mind from the very beginning.
And we've got some questions now in the Google Doc. So Humayun has asked, have you considered causal constraints from human decision makers? If not, what is your point of view on this? So I'm not sure what causal constraints means there, but perhaps as in, I guess, restrictions on what's allowed in the causal model, perhaps. But that's another kind of causal prior knowledge, I suppose.
Yeah, I haven't directly thought about it. It is true that, and I think we are going to have a bit of more discussion this afternoon, how you combine the recommendation of a prediction by the algorithmic system to the recommendation of a human, or how to incorporate restrictions. If by simply keeping in mind the algorithm, things become difficult. When you start mixing the two of them, it doesn't seem to become any easier. So
I should say to people that Isabel is also going to be in the panel at the end. And I think this question is maybe relating to kind of eliciting priors from humans about causality. So maybe something that we pick up in the panel later on. And then there was another question from Jordan Reco. How do we deal with non-Euclidean feature spaces where similarity is harder to define, such as a VAE, for instance?
So right now we are actually not making any assumption on in our subpopulation approach. Actually, what we are doing is to infer the interventional distribution as many conditionals or as many regressors as nodes in the graph, and for that we are using a conditional variation autoencoder. So the parent-children dependency is not restricted to a particular parametric form, but of course, but not restricting ourselves to any parametric form, we can only infer the interventional distribution, but not the counterfactual one, right? So as soon as you want to keep removing some of your assumptions or your limitations, you pay a bit the trade-off by how individualized your recommendations can be.
Great. Thank you, Isabel.